Hello students, welcome back to the session. Let's start with our topic of equilibrium constant. Now we will be discussing about equilibrium constant and how it is favoring the product on one side and again on the reactants on the other side and all the changes which are required to do that. Okay, let's begin with this. So students, now we will be discussing about equilibrium constant. Now suppose that you have this gaseous phase reaction, okay, and the chemist who performed this reaction performed it at a constant temperature of 25 degrees centigrade, that is room temperature. He also recorded certain data. Okay, the first data which he recorded was he took the product concentration 0 and the concentration is given in molarity. So that means there was no product. He first took the reaction, which is fair enough. So he took the reactant and the reactant concentration which he took was 0.67. Now after he performed the experiment, that means he allowed it to rearrange itself, the product of NO2 which he got was 0.0547 moles, whereas NO2 N2O4 concentration remained at 0.643 moles. Now what he did, he divided this two concentrations just like that without obeying law of mass action. So after that, by obeying law of mass action, he computed another value. Similarly, he performed series of experiments by varying the concentration of reactant as well as product and then measuring their concentration again at equilibrium in molarity, of course, obtained a ratio of that and then obtained a ratio through law of mass action, and this is basically Kc, that is reaction rate constant or equilibrium constant, obeying law of mass action. And you can see that it was constant, it was assumed to be constant, having same value throughout it. Now equilibrium is defined by K. Okay, how to justify this expression? Can I say for a general reaction which is A plus B, B times B is reversing to C times C plus D times D, your K is nothing but the concentration of your product raised to the stoichiometric coefficient of that by reactant raised to the stoichiometric coefficient of that. Fine, okay, no problem. So can I say that this, it is involving the concentration as well as the stoichiometric term? So can I say it is nothing but it is defining the entire state of the reaction, the entire state the reaction, as in, you know, the stoichiometric term, that is the number of moles involved, at what concentration they are involved. Thus, in other words, you are defining the equilibrium condition itself. Okay, now can anything be said about or noted about the magnitude of K, that what magnitude will be? Yes, it can be. For example, if you look at this statement which I have underlined, if K is much larger than unity, it is favoring the product. Now how to arrive at that? See, you like that previous example of molecular rearrangement of nitrogen dioxide, you can get the data for other reactions also, compute the value of K and compare it with one, and then judge accordingly that whether the reaction is favoring the product, or if the condition is just the opposite, you can reach this conclusion that it is not going to favor the product but favor the reactants. Okay, after that we can also conclude that the equilibrium constants can be expressed in terms of concentration as well as pressure. Fine, how? Suppose you have a gaseous phase reaction, okay, that the reaction is occurring in terms of gases. Now you are not having concentration data. Somehow you could not measure the concentration of your gases, but on the other hand you could measure the equilibrium pressure or partial pressure of each and every species, gaseous species basically, involved in the reaction. Now all you need to do is to figure out another way to find out Kc. Fine, you can do that. You can do that by using Kp, and Kp is nothing but for a general reaction, if you are going to follow AA plus BB, which is reversing to C moles of C plus D moles of D, your Kp will be partial pressure of C raised to the power of C, partial pressure of D raised to the power of D by partial pressure of A raised to the power of A, partial pressure of B raised to the power of B. Okay, you can easily memorize this with, if you compare it with respect to Kc, which is nothing but in terms of pressure, it is using concentration terms, D to the power D and so on, that is A to the power of A and concentration of B to the power of B, which is their stoichiometric coefficient. So can I say you are only going to replace the concentration with the partial pressure, rest all the law of mass action is going to be obeyed. That means you need to raise the respective terms to their stoichiometric coefficient and move ahead and proceed ahead and get your calculated answer. Okay, this is what the second and the third statement tells. That means Kc uses concentration of the reactant and product to calculate the equilibrium constant, which I have shown you here and also earlier, and this is a new statement right now, that it pressure of the gaseous reactant and product to calculate the equilibrium constant, which I have showed you here, that how it is using the pressure. All you need to do is to relate it, correlate it. Okay, just replace the concentration with the partial pressure and arrive at the expression. That's all you need to do here. Okay, now you can see that the equilibrium constant expressions. Okay, for example, you have this gaseous phase reaction. Okay, so what will be the value of respective K? So Kc, can I say product, which is N2 NO2 or nitrogen dioxide, which I have circled. Okay, and so concentration of the product and its stoichiometric coefficient I have circled here, so it is raised to that, and your reactant, which is this, so the concentration of this, and this stoichiometric coefficient, which is 1, so raised to 1, which you did not need to write. But since it is gaseous, so apart from concentration you can have one more data, which is partial pressure. Let's look at that. Okay, so partial pressure Kp, so partial pressure of NO2, partial pressure of N2O4, and the stoichiometric coefficient of 2 is here, and since its power was 1, no need to write down. Well, so we have seen that how the equilibrium constant expression can be generated by using the simple concept of law of mass action and knowing the stoichiometric equation of the chemical reaction at equilibrium at that particular temperature.